So welcome everybody. Thank you for coming for this last lecture before the holiday break. I'll recap a little bit what we did last time, up until now. So up until last time we defined what morphisms were, and we also used a notion of quasi-affine variety or subset. Right, so it's just an open subset of a affine subset. And it's reducible if we want to talk about varieties. Okay. So basically we have two affine subsets. We could also just restrict to quasi-affine, but mainly the way we define morphisms from one to the other is basically by just saying that if we take a regular function here, so this is let's fix these notations here like this, then we can pull it back. Okay, so we remember that this is a notation for phi conforms with f. Okay, restricted to the relevant sub-open set. And the idea was to say that if we take a regular function and we can pull it back to a regular function, then this will be a morphism. This is like this. And it amounted to saying that if we consider coordinates inside an affine n space, f was given by polynomial functions, basically. Okay. Now, last time I didn't have time to do this, but I wanted to give you, to extend a little bit the idea of what a affine variety was. So this is kind of a regular definition. Basically what I wanted to say was that any topological space with relevant regular functions that is isomorphic to an affine subset of variety is an affine subset of variety. Okay, so why am I introducing this this extra notion that you might think, okay, well, we're not proving anything? Well, I wanted to give an example of something which is quasi-affine.
Isomorphic where? Like is what?
Isomorphic as topological spaces.
Okay.
And we could also talk about the regular functions. But what I wanted to want to do was just to give this example to show that there are some quasi-affine varieties, so open inside a affine subset, which are actually isomorphic to actual affine subsets. So the principal open subsets are affine. This was basically my course. And this is mostly what's going to be of interest for us. Okay, so what does this mean? So you remember that we can define d of f. So these are x in a affine subset. So we could also just affine subset such that f of x is not equal to 0. Yeah? And this is just f which is an element of the coordinate. Okay. So this actually is an open inside of x, right? But in fact, this will actually be even more than that. It will be isomorphic to an affine variety. And the reason I spent so much, I let so much space here, is that actually I'll define here another space, which is inside, well, it's in a space which is one dimension higher than the one x can be embedded. So how do you do it? Well, you take points xt, which are x times a1, such that t times Lx is equal to 1. Okay, and the way you can define a map between the two is simply with by projection. So let's, yeah, this is just a projection, meaning that I take xt and I just associate this. Pretty snap. And it turns out that this space, well, it lives inside of x times a1 of k. Okay, so this is an affine subset. Okay. It's nice, but it's also actually closed. Okay, so basically, we can give actually an extra equation inside of this. So the equation would be t f of x minus 1. So, or you can consider this space as v of this equation inside of this v1. Okay. And it turns out that you can also define an inverse to this, which is also happens to be regular. So you take okay, so you take a point here y, and you define, well, you want the first coordinate to be y, okay, the same point we started from. And the other one, well, quite obviously, it will need to be 1 over f of y. And since we are outside of the zero locus of f, this extra coordinate will be a regular function. So this is good. You can actually draw a picture with this, which is pretty nice. Okay. So imagine this is x. Okay, so x is this one dimension. You could actually just consider the hyperbola. Just a1, and you want to go to look at outside of the origin. So the idea was just to add an extra dimension. So this is a1, and to consider, and here, so the set we are interested in is here. Okay, so this is the of f. And the extra set we are now found ourselves with is something that would look or be similar to a hyperbola. And of course, the projection is just this. And this can be defined by an equation. So something that is quasi-affine can be affine itself. So this is what I wanted to talk about and close the chapter on affine subsystem. Okay. So now we have a good idea of regular functions, but I also wanted to talk a bit about rational and birational morphisms before we go a little bit further on. Okay. So I will set x and y be quasi-affine varieties. Okay? So now we want things to be irreducible because, well, I think we could give a definition of what a rational function would be on something which is not irreducible, but it will be too much extra work, and it's not such a relevant notion anymore. So a quasi-affine varieties, between them you can define a rational morphism phi between x and y. So it's not written like a classical arrow, but more of a dotted arrow, okay, between the two. Let's see. So it's not really morphism per se. It's an equivalence. Equivalence class of morphisms. So what is inside of those classes? We have pairs of u phi of u, where u is an open inside of x, and phi of u is a morphism between u and y. Okay. So this is why we want to have varieties. Is that any, you remember, okay, so still need to be honest. So you remember that when you have something irreducible, any open subset is dense. So this is kind of the idea of what a rational morphism is. It's something that is defined almost everywhere. So kind of like when you do measure theory. Okay. And okay, so what's the equivalence relationship? Well, obviously the equivalence relationship simply says that they agree on the intersection. If you restricted to inter V is actually the same morphism as VB restricted to inter. So this, you remember that when we defined equivalence relationship for local rings, we only wanted to have an open which is inside the intersection, but here, since affine varieties are reducible, we can actually extend the equality to the whole intersection. Yeah. Okay. And okay, so this is one. And what is a rational function? Well, this is just a rational map to the affine line. Okay. So, because, okay, so the affine line always plays kind of the role of the scalars for us. So this is why whenever something arrives in A1, we kind of think of them as functions, per se. Well, there's some subtleties for that one. Maybe we'll talk about that when we talk projective space. Okay, so. Okay, so kind of like what I was saying about this identification between two rational maps like this. There's an important lemma we kind of need to have in mind when we work with this. So consider two two morphisms, okay? Such that f restricted to u is equal to g restricted to u for some non-empty open. Okay. Then f is actually equal to g. Okay, so this is kind of the extension of what the identity property worked for regular morphisms, regular functions, sorry. But this extends to regular morphisms as well. This is not such a big problem. And this lemma actually plays a role in telling us a little bit about how these things are defined. So as you can imagine, that sometimes these rational morphisms, one of the problems with them is that we cannot really compose them. Because why is that? Well, let's take an example, a very basic example. We have x and y, so x is a curve, let's say a1, and y is the plane. So you have an embedding of the line inside the plane. Okay, fine. But what happens if you have another rational morphism, which this time actually is defined outside of this line? You can't compose them, it doesn't make sense. So, in order to restrict ourselves a little bit so that we don't encounter these kinds of properties, we need some extra definition. So, let's start. So the first one is the notion of dominant. Is dominant. Okay. If for some representative of this equivalence class, u phi u, we have phi of u of u dense. Okay. So if we have a dominant morphism here, then any kind of thing that can come beyond y, a morphism that starts with y, could be composed with phi. Okay. And well, okay. So and there's an extra. We can go a little bit further. So this is built by rational morphism. So a is a it's a rational morphism x to y that admits a rational inverse. So what is this? It's a rational morphism from the other way. Such that phi times psi is equal to the identity of y, and psi times phi is equal to the identity of x as rational functions. Okay? Functions, sorry. So what does that mean? That means that actually phi times, you can take a representative of phi, one of psi, and actually if you compose both of them, then they are equivalent to the identity, which is also a rational morphism. Okay. So this is what this composition is. So maybe just to insist that these are equivalence classes, I will take a triple equal. Okay. And in this case, okay, this is the terminology. In this case, x, y are birational. Okay, so this is more or less a geometric logic notion. So, okay. We'll very soon see what this means algebraically. Okay, so one of the main ideas, well, we can prove easily by instance, for instance, using the lemma, by saying that the rational morphism is dominant. Okay, but okay, let's have some quick examples. Okay, so if I take x, which is affine, and f, which is inside of A and x. Then I have the principal open, I have x itself, and the classic inclusion. Okay. So if I consider this canonical inclusion is rational. And okay. And it's actually a birational morphism if you consider that if this is not empty. Okay, so the way we can define that this is not empty is that if I exclude the inverse elements. Okay, so the inverse elements, if I take them away, then this is not empty. And this is a birational morphism. Well, at least it represents a birational morphism. Okay. Well, very often we will kind of have an abuse of terminology by saying that a map will actually be a birational morphism when in fact we're talking about for this class. Okay, so this should be a first example. Sorry about that. So the other example was, if you remember, our cusp curve. Okay, we defined a morphism between A1 and C, which was V of, let's say, x minus y, but y is cubed, x is squared. Okay. So we defined a morphism which is between the two. So if you remember, we have associated t the point to t cubed t squared. We knew that this was not an isomorphism, but this is a birational map. Basic idea is that you get rid of 2 points up and down, and then everything becomes isomorphic. There. Okay. So, what about the algebra in all this? We have defined many algebraic components, algebraic, let's say, objects associated to a fine variety. What do rational maps and morphisms correspond to? Well, this is related to the function field. Okay. This is basically what was left in our lexicon of objects to study. Okay, so K of x can be identified with the set of rational functions. If you remember, we defined K of x as being an equivalence class of regular functions defined at open sets. So this is kind of what this is mostly exactly what happens here. So if you want to think about rational functions, think at something inside of the function field. Okay. Well, the second one is what happens if we take a dominant morphism? What happens between the function fields? Well, it happens that, using expression, well, this corresponds to an injection between the fields, the function fields. So any dominant morphism x y is called phi. I'm alternating between phi and f for the rational morphisms. But okay, never mind. So this thing will induce an injection between the functions, an injection of fields. Okay. So, but this is, as always, it is reversed. Okay. And if we identify rational functions, it's kind of the same thing. So we'll take a rational function on y, so it's something living here, and we pre-compose it with phi. So we pull it back. So yeah, let's pull back f. So, and this defines an injection. Okay. Very well. So, equipped to this machine like this, we actually can define a correspondence. It's how do we look at it in broad perspective. Okay. So if I have x and y quasi-affine this time, varieties. Oh, keep in mind these are varieties. The extra quasi qualification here shouldn't be something you should be afraid of, since all these rational functions are defined on open subsets of the affine variety. So if we restrict to an open for a quasi-affine variety, it's harmless. Okay. And we have the following are equivalent. This is the abbreviation for this. Okay. X and y are rational. Okay, so there's a rational morphism between the two. X and y have non-empty isomorphic opens, non-empty isomorphic open subsets. Okay. Well, this is kind of what this is probably just a translation of what's happening inside this equivalence case here. But mainly, the conclusion, which is very interesting, is that k of x is isomorphic. So if you have one dominant morphism from one direction phi, you take the bidirectional inverse, and these pullbacks define the isomorphism between the two, like this. Okay.
Andrea,
Yes.
I'm not certain if I interrupt you at the right moment, but perhaps it's a good idea to give one more example which will illustrate all these notions, and that's the hyperbola. That's birational to the line. It's a good example that shows an example of a dominant morphism. Of an inverse that's a rational function, and of a birational map. And an easy isomorphism between the function points. Yeah.
Okay.
Yeah. But maybe after you prove this, but I was thinking that in addition to two, like you have two examples, it's also nice to see something that's not theoretically isomorphic.
Oh, wow.
And this is the hyperbola with the lines. I think it's the.
We more or less did it as an example of what at the very beginning, but
okay.
But that's a good idea to bring it back to illustrate it. What happens here? Okay. Okay. So these things, I will not really prove these because it's not that difficult. You could even try to do this as an exercise. But if you want a reference to have a place to go to, use that translation. Chapter 9 is a good case. Okay, so let's take again the example of the hyperbola. It's an even simpler example. So, as you remember, we had, well, it's mostly something to do with this, right? Let's see. Okay. So, remember we had, let's say that this is A1 and this set, okay, is D of X. the one variable, you know, this is associated to the k of x, and you have an element which is x, the function on the whole line, and if I want to get rid of the origin, 0, I just take d of x. So this is a principal open, and as you can remember, we have this isomorphism between the two, like this.
And this is defined as x, y equals 1.
Exactly, yeah. So this, we define it as being y. So this is the set of points x, y in A2, such that x and y are equal to 1. So this is clearly the parameter, right? And we know that we can project it, and the projection y to A1 is birational. Okay. Like that. Okay. So this, because of course we don't get the whole picture of A1. That's always the point that is missing. Okay. Okay. So another one. I have an extra example. So maybe. Okay. I don't know. Take it. Well, so another quick example is, well, it's a partial, it's not the whole thing, but it's a part of the blow up of the origin. So, okay, let's take this as an example 1 and example 2. So, I'll just call it a blow up. Like this, because it's not the whole picture of the blow up, but okay. So I'll have 2 copies of A2, isomorphic, but I'm not gonna, you know, there's obvious maps that you can define between 2, but there's one that is very interesting, which is a this is also called a quadratic or a monoidal transformation. Okay, so this is part of the blow up. You need to go to the projected space to define the whole blow up. But this is kind of what it looks like on the affine space. And this is birational and non-isomorphic. Birational, non-isomorphism. Because its inverse is defined for u and v such that, well, for u is not equal to 0, we just define u and it's v over u. And these are not bijective at all. Like set theoretically, they don't biject at all between the two. Not this one, not this one. So, okay. Yeah, and this is not even injective and not even subjective, because if x is equal to 0, then all points that with x equal to 0 will be sent to 0. So there's an infinite line in the fiber of zeros. And yeah, you could see it like something like this. You have one copy of A2 here, this is the origin, and here everything corresponds to each other except at the origin where there's an extra line added. Okay, but to make sense of what I just said, you need to have, well, we would need to have a little bit more concepts around that.
Maybe it's also good to see the isomorphism on the level of the function fields. In example 1, it's easy to see.
In example 1? Oh,
yeah.
okay.
Yeah.
Yeah.
I mean, it will be a verification of this TFAE, the Gapman's result on the right side.
Yeah.
At least let's verify it in an example.
Okay. And let's verify between the function. FF is just a function. Okay, so the first example, well, the function field of A1 is very simple, right? K of A1, it's just K of I will use the variable x. Okay, so it's the rational functions on x. Now, on the other hand, this variety here is inside A of 2. Right? So, we know that it's going to be a fraction field of something. Then it will be related, I guess. So what's inside of here? Here we have the coordinate ring of y. So this is k of x and y divided by x, y, minus 1. Okay. So this is a prime ideal, this is an integral domain, and so we can take its fraction field, but what is this? Well, another type of notation, you can consider that this is the fraction field of k of x, x minus 1. Okay? Of course, since this is just the projection which takes x, y, and gives us x, this map will just take x, well, this will just take any, it will start from a polynomial x and y, and we'll just restrict it to x, let's see. Yeah, basically, this is what it's going to do. But, oops. Wait, no, this is not.
Isn't it why it gets sent to x minus 1? Or like
Sorry, no, it's the other way around, yeah. It's just f of x, it will be just sent to the same thing. Yeah, it's reversed, I forgot it. I was saying something foolish. And what is so these are the normal polynomials, but if you take their fraction field, well, you can, they will have fractions of two Laurent polynomials, but you can just multiply the denominator and numerator by x to a high enough power, and you obtain something here again. So this is again, oh, yeah, I see why there's some confusion, possible confusion. This is not the notation for the field. This is still rational functions. So in fact, they should be in this direction, and it's actually nice values, right? It's like that. So, okay, let's see. Okay, what about this one? Well, this one is in two variables, u and v. Okay, so here we have rational functions in two variables, u and v. And the other side, we have the same thing. But what's going on between the two? Well, as you can imagine, this is most definitely the map that's going to happen. So if I take f and u, well, a rational function in u and v, this is well defined, you can actually replace u and v by what they are supposed to be here from the morphism. Like this, and this actually admits an inverse. So we take it's just the inverse image of the other one. It's a change of variables that doesn't really affect much of the. So this is at the level of rational functions. So this is inside of a ring. These things are not could be interpreted as something more than just, let's say, functions. Right? These are formal expressions, so this is why these things are always defined. Right? Okay. And these are reciprocal isomorphisms between the two. We could have fun by watching what goes inside of each of one, but I don't think I will have too much time to go too deeper. Are there any questions? for any of what happened just now, or is it? Okay. Okay, so this allows me to go into the last stop before we go deeper into the realm of singularities. So our last, let's say, pit stop for algebraic geometry will be projective space. So this is okay. So this is somewhat of a chapter 4. So this is projective space and projective varieties, of course. So I very often abbreviate projective with just Proj. Okay. Okay. So I've sold you quite often the idea of a projective space. The main idea is to compactify. That means that you have a space, but it doesn't have enough points. That's the common trend that happened. Remember the Bezout example I gave at the very first lecture. So, in order to compactify, we need to find some other points. And these points will be considered as being infinitely far, so points at infinity. So, okay, so projective space should be seen as something like a fine n space plus points at infinity. Let's see what that means in a moment. Okay. So let's give the formal definition. Of course, this is a very formal definition, but for any space E over K define. So we'll often see this letter P with a double H, and this will only be E, where we get the 0, and we quotient by an equivalence relation, where two vectors are equivalent if and only if they are collinear. So this is collinear. Sorry. Okay. So of course, this is a notion that took a while to figure out. We had a lot of axiomatic problems defining about giving us these models for what a projective space should be. So this is why I say that this is a much of definition. Okay. Oh, so mainly we will work with one for a special type of projective space, which is associated to a special projective vector space, which is simply k of n plus 1. We add n plus 1. Why we do that? Well, if we look at the equivalence relation here, so lines through the origin become points. Okay? So in some sense, we contract one dimension. So this is why we need an extra one to hope to have the good dimension. Okay. So this is the projective n space. This is the projective. Right? Okay. Oh, the reason why this is interesting is because things inside of here, we can give them homogeneous coordinates. Just like we work with affine space with coordinates, this has an analogous concept, and a lot of the projective stuff will have analog concepts from the affine world. Okay, so let's say a point A in PFK has homogeneous coordinates write with brackets. Oh, Gatman doesn't use brackets, but I do. If the vector, okay, so if the so I write it as a line, but it should be considered a column vector usually, represents the point A. Let's see. Okay. And place. And the main feature of these homogeneous coordinates is that, well, they don't really have a unique presentation. So for all lambda which is inside of K not 0, we can multiply all of the coordinates by a certain scalar, and we will obtain actually the same point in the projective space. And this is also an equivalent way of defining the equivalence relation inside of K as well. Yeah. So the thing with homogeneous coordinates is that it's almost something that comes from the affine space, but to remember that we deprive the vector space of the origin. So the main idea is to never have all of these things equal to 0. If you have all of these things equal to 0, then this doesn't exist. So, yeah. So this is 1, 2, 3. Okay. So why do we call this stuff affine space with points at infinity? Well, let's unscrew a little bit Pn of k. So we can consider the map. So we will have an of k, Pn of k here. Okay. So we will actually find that there's a copy of n of k inside of Pn of k, which is a very easy way to do. You just take a point with coordinates x1 up to xn. Be careful with how much our index or indices, and define. So if I start with a 1, then it's surely going to be well defined, and well. And you just add the coordinates here. So, okay, we have a point inside nk and have a representative here. Okay. So this is a bijection, okay? It is a bijection between, well, between a n of k, and let's define what's going to be its image. U0, which is, I will start to abbreviate now on these points x, like this. So if I have a representative which doesn't have, this is a weird way to say it, but this is well defined. If I have a point here, it has homogeneous coordinates, and if one of its representatives have x0 not equal to 0, every one of its representatives will have the x0 not 0. So this is well defined. And what is the inverse? So, okay, so I will use the still. So this will be U0. I will use the same orientation between the two. And what's going to happen here? Well, we want something so that if we re-go through here, we obtain 1 here. So we will actually need to normalize these things by x0, so that we have 1 here. We'll just divide by x0 everything else. So this is what's going to appear here. It's well defined, everything goes well. And the main goal of, you know, maybe, yeah, the ambition, let's say, for at least as a first goal for some project space would be to show that this actually, to give the meaning to say that this X is actually an isomorphism. Okay, so this is a bijection. We then need to define what's the topology. So it's a homeomorphism, and then we need to define the regular functions so that we can say that this is indeed a morphism. Okay, so there's still a little bit of work to do. Okay, let's see. Okay. So we need, kind of like what we did for the affine space, we need to define analogous things for P and K. So zero locus, ideal, and great coordinate rings, and for that we'll need to go into the graded world. So, okay, there are terminology, but all these things are going to fit well together, so there's no real problem. Okay, so let's take a polynomial. Okay, is homogeneous, and you have this already, if all of its polynomials, monomials are same degree. Okay. So, for instance, this means that if I take any scalar lambda and I multiply all of its variables by lambda, then what comes out will be p x0, but I'll have to multiply by lambda here, elevated to the degree of p, right? And here degree is a well-defined constant, so that's not a problem. Okay. So the problem is that when we'll define, if we want to define functions on the projective space, considering homogeneous coordinates doesn't give you a function. It's not well-defined. And this is also related to the fact that morphisms from the projective space to anything are constants. But we'll come to that later. Okay. So we need concept of graded ring. So this is a ring R which can be decomposed into a direct sum. So this is an analogy of what's going on with the polynomials and the degree of monomials. Okay? So you'll have a ring, it is decomposed, and RD, it's something inside of R is an abelian subgroup. Okay, that's the minimum one. And for all D and E, we have a sort of additivity of degrees. So if I take an element of R, I take an element of E, then I will end up in R plus E. So this is the multiplication of the ring. Okay, what I'm putting. And RD, these are the homogeneous elements of the of R of degree E. Again. Okay. So there's also this analogy with ideals. So what are graded ideals? Okay, so these are ideals in a graded ring that are generated by homogeneous elements. So, okay. As you can imagine, everything that we need in order to define the analogy with for the projective space will need to go through the of homogeneous homogeneous concepts. Okay, so the standard example is, of course, you have P, the polynomials, and what is the graded decomposition? Well, very simply put, it's simply the homogeneous polynomials. So the terminology speaks for itself. Okay.
Sorry.
Okay.
Okay, so now we have, let's draw x equals 1, or y, yeah, doesn't matter, yeah, or y equals 1. Yeah.
Okay, yeah. First the coordinate. Right?
Yeah, let's draw this line. So now if I think about the set of lines to the origin, yeah, so you see that each line corresponds to precisely one point on that pink line, but yeah, this line here, which is defined by by x equals 0, yeah, it does not correspond to any point on the pink line. So you can think of P1, the set of all lines to the origin, as the union of A1, which is the pink line, and that line x equals 0. And I think maybe very quickly we can do the same thing for P2. This is what I do usually with my students. So P2, now we have 3 space.
Okay, so this time I'm going to point it horizontally because it's complicated.
And so now let's pick, exactly, let's pick this parallel plane. And so now we think of the set of lines through the origin.
This is the origin.
Right, and so, almost all of them, they intersect that plane. The only lines that do not intersect that plane are the lines that lie in the z equals 0 plane, But these lines that lie in the z equals 0 plane, this is precisely P1 by the previous example. So we get that P2 is a union of P1 and A2. So maybe we can just write this P. Exactly, and maybe we can just write the unions, like P2 is the union of,
So actually, I was going a little bit too fast.
No, I think it's a good thing to remember because, so to have the geometric picture also in mind. Yeah, very good, thank you.
Okay, so this is So was that recorded? No.
It was, but I can cut it out.
No.
No, it's important. This is a very nice drawing. Actually, there's even another version of this with the stereographic projection and a variation of the stereographic projection as well.
Yeah.
That's okay. So
If you think you have time to do that, do it because
okay.
these are really nice geometric constructions.
Oh yeah.
So let's do it. Let's do it.
Okay. The speaker is always the cook, right? And you are supposed to eat what he's giving. Okay. It's not a perfect circle, but almost. So, okay, I'm doing the horizontal version again. So this is x, this is y, okay? So the main idea here is that, okay, maybe it wasn't such a good idea to do it like this. Okay. So as we consider, we have points that correspond to lines. You can consider them as points on this line here, but you can also consider them the intersection points with the sphere itself, right? So all of the points which are not horizontal will intersect, will go for the origin and another point here. But what happens with the x-axis? Well, it will be equal to tangent. So in fact, this kind of, if you look at this in C2, you can in some sense say that P1 of C is isomorphic to the Riemann sphere, if you want, or simply put, you just take the compactification of C, which is C adjoin a point at infinity. And the point at infinity should be seen like this point here. Like that. There's another version of this is one version of this stereographic projection, but there's another one where we put the circle at the center, the center of the circle at the origin. But yeah, I like this drawing as well because it kind of has this nice picture where everything is in frame. Okay. So these are nice pictures that you could have for, so this is more, let's say, topological or analytic version of what we're saying here, like that. Okay. And this is why also we talk about compactification, because for the complex numbers, this is actually what's going to happen. And the projective spaces, they have a topology, and they are actually compact manifolds.
But this compactification is in the analytic topology of C, right? So
This, yeah.
because it's a risk, it's already compact.
Yeah. Well, you know, everything is kind of smashing all together because the compact. Oh, okay, so yeah, I see what you mean. It's it's
quasi-compact, right?
Yeah. We haven't talked about complete varieties. Yeah.
Excuse me, may I also
Yes.
add a comment?
Yes.
There is a simple decomposition for the projective quadric, which is a disjoint union of an affine quadric with the same dimension and quadric with minus 1
Minus 1. You
one less
mean
dimension.
this quadric? This one? I don't know.
If we consider a projective quadric,
Okay.
that it can be decomposed as a union of a affine quadric
Okay.
and disjoint union with a quadric with one less dimension. So it is, I think it's a construction due to Klein.
Okay, I see. Oh yeah, well, you add the, yes, it's actually quite, yes, I see what you mean. It's, it will be very interesting to, actually I remember this example because
The simplest thing is, for example, the parabola.
Yeah.
You add the point at infinity.
I
and
need
close
to,
it up.
I need to introduce homogenization, dehomogenization.
Yeah.
This is what I was going to. Okay. Well, yeah, it's no, this is interesting because you know I was going through these very dry algebraic concepts, but this is beneath all of this. These are pictures that we're dealing with. Okay. So inside of these things, we can define varieties as well. So, okay. Once we have ideals, well, homogeneous ideals, you can do many nice things with them. So, if I have G and a subscript, which may be nothing, actually, homogeneous ideals. I can do many operations between them. So one of the things you can do is like add them together, multiply them together, consider the intersection, or even take a radical for these ideals. Well, they are still homogeneous. The only one, all of these are pretty easy to prove. The only one which is a bit more difficult is this one, but okay. There's a nice characterization of homogeneous ideals is that G is if and only if. If I take an element inside of G, which is decomposed, right? So f of D is inside of Rd, okay? So if I take an element which decomposes into homogeneous components like this, then all of its components will be inside the ideal as well. So this is summed up in saying that the ideal has its own graded decomposition. Like this. Okay. It's a nice exercise. So unfortunately I have to erase this nicely. Okay. So okay. Well, yeah. Well, it seems that they don't want to raise themselves, right? Okay. So now we can define like okay, so these are divisions. So now I'm going to bombard you with all the definitions that are that come with all these things. So I have a zero locus of an ideal in K if not an ideal but set of homogeneous polynomial. So sometimes I'll have to make the difference between the projective and the affine. So sometimes I'll add the V inside, just here, but most, if there's no confusion, this will just be written as V. So this is the points inside of P and of K, such that f of x is equal to 0 for all f in S. So remember what we said about homogeneous polynomials is that if I consider two distinct representatives of homogeneous coordinates, they differ by a non-zero constant. So saying that something is 0 or not 0 is well defined here. Okay? So I can define its zero locus like this. What about the ideals? Well, since I will only focus on homogeneous ideals, as you can imagine, they are generated by the homogeneous elements. So if I just look at the homogeneous elements inside the homogeneous ideal, then it's also well defined. Okay. Set or define the so f of x is equal to 0 for all f inside of G, which is joint homogeneous like this. Okay. So these are called the projective sets. like what we had with affine sets called the projective. Sometimes I'll draw the sub like that. Okay, so these are the elements in the projective space. Then we can go back to an ideal. Okay, let's say okay, define. So sometimes just I did with the V, I'll write I P, but usually I just write it like this. So this in term. Okay, so there's. Okay, so I'm sorry, it's stuck. I went a little bit fast. So I will take all the polynomials inside of K of X. Okay, which are homogeneous. Okay, such that f of x is equal to 0 for all small x in x. But you can imagine if I restrict myself only to homogeneous polynomials, this is not an ideal. This is not stable under addition, for instance. So what I do is just take the ideal generated by this. So that this makes sense, right? Okay. Well, yeah. Okay, so okay. So fine. Now, one of the interesting ideas to prove is that a lot of the properties we'll manage to prove for the projective spaces will be done by bringing it back actually to the affine space. So let's see, this is 3, this is 4. Okay. So let's consider the projection map. Okay, so here we'll have Pn of k, okay? And you know that you remember that this is defined as an equivalence class over k of n plus 1. But let's consider kn plus 1 as an affine n space. Okay? So we need to get rid of 0. So this is going to be P, or pi, sorry. P is in French. So this just takes a point and assigns the homogeneous coordinates. Next. Okay. So this is an important map because most of the properties will have involved these ideals will be, let's say, lifted up to n plus 1, and then you will use all the properties established there to bring it back and bring them back down to Pn of k. Okay, so this needs a little bit of things. I'll draw a picture of what this kind of looks like afterwards. So a cone in, let's say, n plus 1, yeah, is a subset such that for all x inside of x and for all lambda inside of k, 0 included this time, okay, lambda x is still in x. So this is stable under multiplication by a scalar. So you can consider X as being somewhat of a union of lines going to 0. Okay. And okay, I'll give some notions and then we'll see what this means afterwards. Okay, so for such a cone, define its projectivization. Okay, so what is this piece? Well, it will be something P of x. So I will need to get rid of 0, okay? Because then I'll just take P of this thing, okay? Okay, so this is inside of P, okay? Like this. Now, if I start with a affine subset, okay, so if let's say if x is affine, it's an affine cone, sorry, and P of x will be a affine subset, then this will be a projective set. We'll see what I mean by that just afterwards. So, and I can go the other way around for a projective subset of P and K. I can define its okay, so the other way around is for a subset Y, define its affine cone, which is P minus 1. So, okay, so this actually has a notation. So this is going to be just the cone of Y. So this is going to be P minus 1 of Y, but we won't have 0, so we need to add it artificially. Okay, so what does this look like actually? Well, so now we need to imagine that this, what I just drew here, is something like P2. So it goes on forever. Not only it goes on forever, but it can act, in some sense, it folds back on itself at infinity. Okay, so very complicated stuff. But just consider a place like this. Then consider subsets inside of this this plane, right? Now remember that the picture we erased back. Remember that I had the origin going through somewhere here, right? Yeah. So this whole picture is supposed to be in a free of K, okay? And this is only part of the projective space. Okay, so what's going to happen if I take this is the origin, okay? 0, if you want, this. Well, the cone is going to look something like this. I take a point on this curve, so this is y, okay, this is like this. I'll take a point on the curve, and any point that is collinear with this vector in A3 is going to be in the cone. So I need to trace, to at least draw this line. And then I'm going to draw for this for every point on this small curve, this small red curve. Okay. and be careful about how this is drawn. Okay, so this looks like this. You'll have points behind. You'll have points going for here. This is kind of something. Well, it's not tangent because this is just the way it's drawn. But then you have points which are behind as well, and so on and so forth. So what I'm drawing in blue is actually just imagine a line going through the origin. Imagine you are here, you have a lampshade, and you are trying to trace with your lamp this curve in this plane here. And the set points that, and the illuminated points will be the cone. This is the cone of light. Okay. Like this. And in a, let's say, reverse manner, if I have a cone or something which is like this object here, I'll just take its trace onto this piece of the projective space to give me what's supposed to be associated there. Okay. So this is a nice let's say a pretty nice object, but there is one code that we need to get rid of because there is one special code that is associated with one ideal. This is called the irrelevant ideal, and the cone in question will be the origin. Now there's just one cone that is problem. So this is called the irrelevant ideal. We could call also the irrelevant cone the origin, but just can't call it origin. Is okay, so like this. Very well. Now, the reason we introduce these things is because now we are equipped with the good notions that can give us the projective notion. So let's make some room, and yeah, maybe that'll be a good place to start. Okay, but okay. So as I was saying, this is actually a very strong connection between the cones and the projectivization. So much so that actually there's a bijection between the two. Okay. There's a bijection between what? On the one side, we have affine cones in n+1. So when I say affine cones, these are affine subsets, which happen to be also affine subsets. No, yeah, okay. So this is the bijection, and on the other side we have projective subsets in En. Okay, so as you can imagine, I take X, I take projectivization, I take Y, I take its cone. Fairly standard. But let's see. Okay, so I need to get rid here. No, sorry. This is where I didn't think it through. Let's see. Okay. No, sorry. I don't actually need to get rid of the origin here because I could take the antiset and the cone could be just the zero because the only correction I wanted to say is on NTN. Then we have very similar stuff as we did for the affine varieties. So if I take, let's see, which one is it? if I take a projective variety, I can take its ideal, then I can take the zero locus. Well, I end up again on Y. Any projective sets. Okay, that's fairly standard. Now, for the other one, so if you remember that was the hard part of the Nullstellung Satz, we had to deal with radical ideals, and sometimes we can take ideals. Okay, so for any you can imagine this will be a homogeneous ideal. This could be different from the irrelevant ideal here, but its radical could be equal to the irrelevant ideal. Okay, so we need to exclude these cases. Okay, such that G for any such ideal, then if I consider the ideal of the zero locus, then I get the radical. And the idea is to bring everything back to the fine cone. Okay. Okay. So, we then, build the correspondence, okay, which is between, so we have projective subsets P and K on one side, and the other side is radical homogeneous ideals in case different from the irrelevant one. Okay. So of course we have Y here, the idea on one side, and an idea here, the zero locus on the other. Okay. So now, as you can imagine, we can then do everything we already did in the affine space, beginning with this, is define the Zariski topology, define what irreducible means, then we can talk about the dimension, which can be brought back to the cone. So the dimension will be just one less than the dimension of the cone associated to it. And so we could really use all of that back in these concepts. Let's see. How much time do I have yet?
Maybe it's a good point to stop the.
Yeah. Then I'll have to. If I start something else, then I'll have to take too much time. So I think I'll stop here. When we come back in January, we'll finish what we had to. We'll finish everything I had to say about projective space. Then we'll finally go deeper into the singularity. Okay, I'll stop here. Thanks.
Maybe I can say a few words before we end the course for this year. So all the recordings, all 4 lectures will be available on the YouTube channel of the center, right, by the end of the week, or even tomorrow. So you can, if you missed a lecture, now is the time to watch it. So I wanted to make a final comment. So today the notion of birational equivalence, or like birational maps, was introduced. So this is one of the kind of greatest problems in algebraic geometry is the classification problem of varieties of two birational equivalence. The other comment I wanted to make is that after Andrei introduced the notion of morphisms between algebraic varieties and the correspondence between the function fields that induces immediately a map between the function fields, this is one instance where you can see really the power of algebra. I want to give the following example. So suppose you start with a surface in a three-dimensional space, so you look at two-dimensional object. I think it was an approach that goes back at least 2,000 years ago. Like the way people study these kind of objects is by projecting to the plane, right? So you project to the plane, you look at the projection, you make a conclusion. If you look on the algebraic side of this, so that will correspond to a map, an inclusion map of two fields. And one field, the larger field, will be a finite extension of the smaller field. So this already brings field theory, like something that was developed in the last, let's say, 200 years.
Yeah.
And even more so, if you make some generic assumptions on this map, this becomes a problem of Galois theory.
Actually, the Galois theory could be considered as the zero dimension of birational classification.
Yes, yes. So this is extremely beautiful connection between geometry and algebra. You know that Galois theory arose from, like, for the purposes of a completely different problem, and yet there is this connection that I think it was the time to at least bring it up. So now we have the language to talk about it.
Yeah. Actually, one of the first steps for singularity theories will be the classification of function fields or curves. That's one of the achievements. So that's actually a very relevant point to bring up, because function fields of curves will just be extensions of K with transcendence degree 1. So classifying curves is brought back to classifying these types of fields. And we'll see that it's a very beautiful problem that, this specific problem with classifying fields of dimension 1, basically, was more or less achieved in the 19th century. So it's very recent that we have this. It was more or less what Riemann did.
Oh, recent for mathematicians, that's the reason.
Yeah, recent. And then in the more abstract approach, so Riemann did it for what we call Riemann surfaces today, but what Dedekind and Weber tried to do was try to give a more abstract approach that could be used, for instance, in arithmetic geometry. And this is more or less what I will try to do by introducing valuations, actually, because that was their approach at that specific case. Okay.
Okay. Yeah. Well, let's take the break again.
One for next year.
Yes.
Yes. We prefer to take it to